Welcome, students, to the latest of our Chapter 6 discussion on the reactions of alkynes. Now, before beginning this lecture, I kind of want to tell you guys a story. Many years ago, one of my older brothers worked on an assembly line at a cookie factory. He was asked to train a recent hire, and consequently took this new fellow to the factory floor and put him in the position that the supervisor had designated. My brother, having the responsibility to train this new employee, informed him that his job would be to just grab the cookies as they came off of the end of the assembly line, put them in a box, close the box, and then push the box into a stack of boxes where someone else would then organize and take care of them. My brother then supervised the man for a short while to ensure that he was doing all right, and then went back to his regular post. After about an hour or two, this new employee kind of snapped. While he was doing the monotonous labor that is typical of assembly line work, moving cookies into this box and pushing the box aside, he just got to the point where he freaked out and screamed at the top of his lungs, "Why are you making me do this?" And then he ran out of the factory screaming and never returned. I'm not sure if that's actually funny, but dang it if I don't love that story. Now, I don't want you guys to feel that way when you're doing chemistry, but if you ever do, please take a break and be sure to come back afterwards. Following this lecture, you should be able to correctly draw the mechanisms and predict the products formed when alkynes are reacted under hydroboration oxidation conditions, alkynes are treated with H2, hydrogen gas, and a metal catalyst. You should also be able to explain why alkynes' terminal protons are more acidic than alkenes, which are more acidic than alkanes, explain how to alkylate terminal alkynes, and design simple syntheses using alkynes. With that said, let's go ahead and get started with our very first reaction, adding H2O to alkynes. Now, before I vault into this, I want to first of all remind you of a reaction that we discussed in our previous chapter, talking about adding H2O to alkenes. I know you've seen this before, but I think the review would be beneficial. When we have an alkene, such as the one shown here, and we add water and a catalytic amount of acid, what ends up happening is we add hydrogen to the carbon that has more hydrogen stuck to it, and we add an OH to the internal carbon. Mechanistically, that occurs in this manner. I have pi electrons on this carbon-carbon double bond floating in the presence of catalytic acid. Those pi electrons come out and attack that proton. The proton now has a choice to bond with carbon 1 or carbon 2. Which one does it bond with? Remember, whichever carbon it doesn't bond to ends up getting a positive charge. Thus, the hydrogen ends up attaching to the carbon that has fewer carbons attached to it. That is carbon 2, giving us this intermediate. The reason is because it leaves me with the more stable carbocation at position 1, according to Markovnikov's rule. At this point, water, which is the solvent in this reaction, thrusts its electrons down into that hole, forming a bond with that positively charged carbon and giving me this intermediate. This oxygen is, of course, still in possession of a full octet. It's only positively charged because oxygen doesn't like having 3 bonds. When a second molecule of water comes in, electrons grab that hydrogen, push these electrons up into that positively charged oxygen to quench its charge, and gives me the final product. It also generates in the process hydronium, H3O+, which can serve as the source of H+ in the next catalytic cycle. Thus, we see that the OH always ends up going into the more substituted carbon, that is, the carbon that would give the more stable carbocation intermediate, which in examples like this is the internal carbon, while the hydrogen from the acid ends up going on the external carbon in the carbon-carbon double bond. So what happens if we add H2O and catalytic acid to an alkyne? Well, let's take a look. Here is an alkyne. Catalytic acid is floating in solution, and what's going to happen? Of course, the pi electrons are going to come out and attack it. Hydrogen has a choice. Does it bond with carbon 1 or carbon 2? Of course, we have to remember that whichever carbon it doesn't bond to ends up with the positive charge. The hydrogen therefore bonds to carbon 2, the carbon that has more hydrogens on it, according to Markovnikov's rule, because doing so leaves me with a positive charge at the more stable secondary carbon. At this point, we can imagine water coming in, thrusting lone pair electrons from the oxygen into that hole to give me this type of intermediate. As we saw with the alkene before, a second molecule of water can now use its electrons to grab that proton, push these electrons into the oxygen to quench that positive charge. giving us this product, along with hydronium to catalyze the next cycle. Now I want to point out something very, very important. This type of product right here is called an enol. The reason is because it has an alcohol and an alkene together in one molecule. We take the word alkene and the word alcohol and squish them together into one word. The word is enol. One thing that you should remember, in fact, as my students, I beg you to remember, is that enols like this, where the OH is coming directly off a carbon that is doubly bonded to another carbon, only exist transiently in solution. Why? Well, the reason is because these pi electrons will come out very, very quickly and grab the hydrogen stuck on the OH, forming a bond between this hydrogen and this carbon right here. Upon doing so, these electrons get thrust down here like a door swinging on a hinge to form a carbon-oxygen double bond, giving me this product. This product is called a ketone. Thus, in reality, anytime we see a ketone or an enol, these two molecules are actually going back and forth to some extent, but they linger much more prevalently at the ketone position. And the reason is because a carbon-oxygen double bond is much more thermodynamically stable than a carbon-carbon double bond. Thus we see ketones isomerizing back and forth to enols, with the enol form existing just transiently relative to the ketone form. This process of going back and forth is called keto-enol tautomerism. I want you to remember now, if I see an enol, that is an OH stuck to a carbon that's double bonded to another carbon, what I really have is a ketone. That will become extremely important momentarily. Before getting to that, however, I want to tell you something that I sort of lied about at the beginning of the slide. The real reaction conditions that are needed in order to push this reaction forward require a little bit more kick than just catalytic acid and water. In fact, if you take an alkyne and treat it with catalytic acid and water, it will not proceed forward with this reaction as effectively as it will under these conditions. What we do is we take our alkyne, we add acid, and the acid we usually choose is H2SO4 with water, and we have to add mercury sulfate as a catalyst. It forms an enol, placing the OH at the more stable internal position, and then this enol instantly tautomerizes to form a ketone. So the real mechanism is a little bit more complex than the one that I showed on the previous slide. However, I showed you this mechanism because I think it's easy to understand if we remember the analogous mechanism with alkenes. Pi electrons come out, hit the proton. Proton goes on the position that gives me the more stable internal carbocation. Water comes in, another water deprotonates, gives me the enol, and then the enol rearranges to form the ketone, according to this thing called keto-enol tautomerism. So to summarize, as we already discussed in an earlier chapter, if you take an internal alkyne like the one shown here, treat it with aqueous acid and mercury sulfate, it will make a mixture of ketones, with the carbon that was originally on the left side being double bonded to an oxygen in the product, and the carbon that was originally on the right side of the triple bond being also double bonded to an oxygen in the product. So we get these two separate products in mixture. In contrast, if you treat a terminal alkyne under the same conditions, it will generate only one single product, this methyl ketone. Okay, so the reason that I bothered to review what happens when an alkene and an alkyne are treated with aqueous acid is because I want you to be able to clearly contrast and compare those reaction conditions with hydroboration oxidation. Now, as we discussed in our previous chapter, and I've just reminded you, if we take, once again, a regular alkene and treat it with aqueous acid, what ends up happening is we place an OH on the internal carbon, the one that would generate the more stable carbocation intermediate in the mechanism. Now, I brought this up in our last discussion. What if I wanted desperately to put the OH on the other position rather than putting it on the internal carbon? Is there anything that I could do? Well, Markovnikov's rule would dictate under these conditions the answer is no. Fortunately, there are other conditions that can yield that result. They are called hydroboration oxidation conditions. Thus, by a mechanism that I do not require you to know, you can take a simple alkene, treat it under these two steps, and place the OH in the anti-Markovnikov position. Now, one thing I want you to remember about hydroboration oxidation is that this is indeed a two-step reaction, so you should not forget to number the reagents. Step 1 is borane and THF, and step 2 is peroxide, hydroxide, and water. Now, what in the world happens if you treat an alkyne under similar conditions? When you treat an alkyne with aqueous acid and mercury sulfate, it ends up placing an OH in your product on the internal carbon, the one that would once again generate the more stable carbocation intermediate, which is completely analogous to what occurs when you do the same conditions to an alkene. This molecule is an enol. In particular, it's an enol that has the hydroxyl group attached to one of the two doubly bonded carbons. As I mentioned earlier, enols instantly tautomerize to form a ketone. Now I should point out that this arrow on the top should actually be larger than the arrow on the bottom, because although these go back and forth, the keto form is much more stable and exists much more prevalently than the enol form. Now, what if I take an alkyne and I treat it under hydroboration oxidation conditions? Well, as occurs with alkenes, if I take an alkyne and I treat it under these same hydroboration oxidation conditions, what forms is an enol where the OH is put on the external carbon in the original carbon-carbon triple bond. In other words, I've just generated the analogous anti-Markovnikov product. As with the reaction we just showed up here, this enol instantly tautomerizes to form this compound, which is called an aldehyde. An aldehyde is different from a ketone because an aldehyde has a hydrogen coming off of one side of the carbon that's doubly bonded to an oxygen. Once again, these equilibrium arrows should show a larger arrow on top than on the bottom, indicating that the equilibrium strongly favors the product aldehyde. So this is what happens in the hydroboration oxidation of alkyne, and I hope that you can clearly see how that compares and how it is analogous to the hydroboration oxidation of an alkene. As with our alkene discussion, you should not forget to number the reagents in hydroboration oxidation. This is a two-step reaction. So to recap once again, if I take an alkyne and treat it with water, acid, and mercury sulfate, I will generate an enol that has the hydroxyl group on the internal carbon, the one that would have the more stable carbocation, which instantly tautomerizes to form a ketone. In contrast, if I treat the same alkyne under hydroboration oxidation conditions, the OH ends up going on the external carbon, which also instantly tautomerizes to form this product, which is called an aldehyde. We now return to a subject that I talked about in our last chapter's lecture, the hydrogenation of alkynes. As we discussed before, if you take an alkene and treat it with hydrogen gas, H2, and one of these four transition metal catalysts, palladium, platinum, rhodium, or nickel, what occurs is it converts the alkene into an alkane by placing these two hydrogens on the same face as each other. That is, they go cis to each other, as pointed out here. So you might be wondering, what happens if I hydrogenate an alkyne? If I take an alkyne and treat it with hydrogen gas and any of the same metal catalysts, it actually converts the alkyne all the way down to the alkane by adding two equivalents of H2 to this triple bond. In other words, under these conditions, there's no way to stop at the alkene. But what if I want to stop at the alkene? Is there any way that I can take this alkyne and just add two hydrogens onto it, converting it to an alkene, and have it stop reacting? As it turns out, there is. If you take an alkyne and treat it with hydrogen gas and a special catalyst called Lindlar catalyst, which is a less reactive form of palladium, it will add the two hydrogens cis to each other and stop at the alkene, giving you a Z-alkene, as shown here. That is once again summarized in this figure. I take my alkyne, hit it with hydrogen gas and Lindlar's catalyst. I can place two individual hydrogens on this carbon-carbon triple, reducing it down to a carbon-carbon double. The two appendages in the original alkyne always end up being Z to each other. Now you might be wondering, what if I don't want a Z-alkene? What if I want to take my alkyne and I want to turn it into an E-alkene? Is there anything I can do there? Well, as it turns out, there is. If you take your alkyne and treat it under these conditions, sodium or lithium and liquid ammonia at -78, you can actually put two individual hydrogen atoms on this carbon-carbon triple bond and give yourself the E configuration, giving you an E-alkene. these conditions stop there. So these are two different ways of taking an alkyne and converting it into an alkene rather than going all the way to an alkane, which is what would occur under traditional hydrogenation conditions. For this second reaction, I should point out that I do not require you to know the mechanism of it. If you want to learn it, however, it is found in your text. And now to a different subject, acidity of alkynes. Now, one thing that I want to point out is that carbon atoms' individual levels of electronegativity actually vary depending upon their hybridization. This is something that I want you to memorize. sp hybridized carbons are more electronegative than sp2 hybridized carbons, which are more electronegative than sp3 hybridized carbons. Now you might be wondering, why in the world is that the case? Well, an sp orbital is 50% s and 50% p. An sp2 orbital is 1/3 s and 2/3 p, while an sp3 orbital is 25% s and 75% p. Why in the world do we care? Well, as it turns out, s orbitals are closer to the nucleus of the atom and are hence closer to the protons found in that nucleus. Hence, if you have an orbital that's sp, in other words, it's made 50% of an s orbital and 50% of a p orbital, it has more s character, which means that it is closer to the nucleus of the carbon atom and closer to the protons. What in the world does that mean? It means that the electrons are going to be sucked more tightly than they would in an sp2 or an sp3 orbital. That ultimately means, once again, that an sp hybridized carbon atom is more electronegative, that is, it sucks electrons towards itself more, than an sp2 hybridized carbon, which is more electronegative than an sp3 hybridized carbon. Now this prompts me to remind you of something I taught you back in Chapter 1, where you might remember me talking to you about something called a pKa value, which are numbers that are used to reflect a compound's acidity. You might also remember me telling you that the lower the pKa value of an acidic proton, the more acidic that proton is. With that said, I'm now going to show you the relative pKa values of alkynes versus alkenes versus alkanes. As you can see here, alkynes have pKa values of about 25. What that means is that these protons here and here, which are bonded to the sp hybridized carbons in this alkyne, are somewhat acidic. By comparison, the protons bonded to the sp2 hybridized carbons in an alkene have pKa values of 44. Protons that are bonded to sp3 hybridized carbons, as in alkenes, have pKa values above 60. What in the world does that mean? Well, once again, this means that the protons which are bonded to the sp hybridized carbons in an alkyne are about 10 raised to the 20th power times more acidic than the protons that are bonded to the sp2 hybridized carbons in an alkene, which are in turn about 10 to the 20th power times more acidic than the protons that are bonded to the sp3 hybridized carbons in an alkane. What in the world do these numbers really mean? Well, looking at an alkane, for example, if I have a pKa value of about 60, what that means is that if you had 10 raised to the 60th power molecules of an alkane, now you can imagine how large that number is. That's 10 with 59 zeros after it. That's a very, very huge number. If you had that many molecules of that alkane, one of those molecules in solution would be deprotonated. That's how unacidic an alkane is. By comparison, once again, an alkene is about 10 to the 20th times more acidic, and an alkyne is 10 to the 20th times more acidic than that. Now, why in the world do we care? Well, as it turns out, because an alkyne has that level of reasonable acidity, we can do cool reactions to it. If I have an alkyne, for example, whose acidic terminal proton has been removed and replaced with a negative charge, I can react that terminal negatively charged alkyne with an alkyl halide, such as this alkyl bromide, and increase the length of that alkyne. Here's the mechanism by which that proceeds. the now lone pair electrons on this sp hybridized carbon, left over when that carbon's hydrogen was removed, come in and attack this carbon right here. When they attack this carbon here, it forms a bond between the carbon in the alkyne and the carbon located here. As these electrons come in and attack this carbon to form that bond, the two electrons being shared by this carbon and this bromine get pushed into the bromine and release it as free bromide. This thereby extends the length of this alkyne to be that shown here. So yes, we can add carbons to the end of a terminal alkyne by removing its proton and then stirring it in the presence of an alkyl halide, like an alkyl bromide or an alkyl chloride or an alkyl iodide. This process is called the alkylation of alkynes. Now just so you know, the word alkylation just means adding an alkyl group to something. And an alkyl group is basically a hydrocarbon chain, a chain of carbons and hydrogens. So you can see I can start with a boring terminal alkyne, hit it with a base that removes its acidic proton, and then the resulting negative charge can then be allowed to attack an alkyl bromide to thereby extend the chain and give me a lengthened overall alkyne. Once again, this process is called alkylation. So I hasten to mention that the base that's usually used to remove the hydrogen attached to this sp hybridized carbon on a terminal alkyne is a base that's called sodium amide or sodamide, whose formula is NaNH2.